build, connect and support multidisciplinary events, multidisciplinary research communities, and we do that through putting on a number of different types of events throughout the year. So we run talks like this one, the seminars. We provide training throughout the year of all different kinds of levels, entry level statistics and data science, right up to kind of the cutting edge methodologies of the day. We run a support service which we call Ask JGI, where anyone in the university can email or message in or phone a query to our team of data scientists and software engineers, and we try to respond as quickly as we can. Sometimes those queries turn into collaborative projects which have been enormously successful, externally funded through partnerships with research councils, for example, charities or our industrial partners. We also act as the portal for the university's relationship with the Alan Turing Institute. The Alan Turing Institute is the National Institute for Data Science and AI. I am the lead fellow, the Turing University lead, managing that relationship, and our institute manager, Patty Holly, is the university liaison manager for that relationship as well. So if you have queries about the work of the Turing, we're your port of call. We refresh our strategic priorities every year. Our priorities for the last couple of years have been as follows: societal challenges, data visualization, reproducibility, and data governance, and fundamental research across the disciplines. As I'm sure you all know, data science is a family of disciplines working together, stretching right across fundamental methodologies in mathematics and computer science, for example, through to application areas across the suite of the art sciences, humanities and social sciences. And we represent all those parts of the discipline across the university and in our activities beyond. Thanks, Jib. Just the last slide. Last of my 3 slides. Thank you. So this is one of 13 events that we're running through the year. At no point me really advertising the ones that have already happened. I hope some of you were able to join us for those. But here we are, Thursday. After this talk, we've got the Library Research Services talking about managing sensitive research data, and later on today, an introduction to deep learning, and 3 more events that might interest you tomorrow. It would be really great if you could respond to our request for feedback after this event. This is the first time, as all of us, I'm sure, have been so deeply immersed in remote accessing events like this. Really great to know how the experience was for you, the platform, the challenges, the benefits of working like this. What other kinds of events we might be able to put on that would interest you and your community would also be really interesting. And if you have any queries about the work of the JGI or the Turing or data science at Bristol, don't hesitate to drop us a line. Okay, so I will now hand over to our speaker this morning, Dr. Gibran Hemani, who is Senior Research Fellow at the MRC Integrative Epidemiology Unit here at the University of Bristol, the Henry Dale Fellow from the Wellcome Trust and Royal Society on the topic of high-dimensional causal modelling, and the talk is on new data on COVID-19 is undermined by old statistical problems. Over to you.
Thank you so much. Can you hear me okay?
Yeah, loud and clear.
Great. Okay. I really appreciate the opportunity to talk to you about this. It's something that happened quite serendipitously that we started working in this particular area. But hopefully it's of use to people to think about the sorts of problems that we've started becoming aware of in the last few months. So new data on COVID-19 is undermined by old statistical problems. So this is a brief outline of what I'll talk about. So first, I just want to introduce the idea of selection bias. I'll just do that with some sort of classic examples. Then I'm going to spend a little bit of time talking about different COVID-19 epidemiological study designs and how selection bias is relevant to those. And I'll spend a little bit of time talking about how to mitigate the problem. Okay, so this is a very famous way of talking about selection bias. It's a specific type of selection bias called survivorship bias. And the story goes a bit like this. It's World War II, and bombers are arriving back to air bases, and they sustain damage. And the question is, how should we armor the plane to improve the safety, improve the to reduce the chance of bombers being destroyed while they're in combat. So lots of bombers come back, and you can map where all the bullet holes are on the plane. And what the US military was going to do, I think it was the US, I think so. Um, they were going to put armor where they found the most bullet holes. And they consulted with a statistician called Abraham Wald. And Abraham Wald pointed out that every plane that comes back has survived being hit. And if you find that there are places which never get hit in the planes that come back, then those are the places that are fatal. Like you can't afford to have any bullet holes in those places. So you should put the armor where there aren't any bullet holes in the surviving planes, which is a very nice way of a non-intuitive way of thinking about the data that you have available to you. And that's basically the crux of the talk. The data that you get access to gives you a distorted view of the world. And you have to be able to extrapolate back to the true world view from a very small selected aspect of what has actually been made visible to you. So they took Wald's advice and they put the armor where, you know, which is intuitive, like in the cockpit, on the engines, where there weren't any bullet holes in the surviving planes. Another example, and this is a bit more subtle. So suppose that you're asking, this is known as the class size paradox. So suppose that you're asking the question, what is the average school class size in the UK? So you might pursue the question this way. You ask a random set of people how many people were in their class at school, and then you can take an average of those answers. Now, this would be wrong. This would give you an overestimate of the average class size. So why is that? Well, here, the target sample, the target population isn't people in the population. So you've taken random people in the population, but that's not what your target is. Your target is one person from each class, because to get the real average estimate of the class size, you need to have each class represented once. When you randomly choose people, you're more likely to choose people who are in larger classes. Now that's really hard to get your head around, but imagine if there were only two classes. One had 99 people and one had one person. The average class size is 50. But if you chose a person at random, you're almost like 99% probabilities you're going to choose the person from the large class. And if you ask them what their class size is, they'd say it's 99. If you did it again, you'd probably get another person saying 99. So you'd get an average class size of 99. And that's basically because in the sample that was available to you, you overrepresented people in larger classes. So it can be quite subtle, and this can, again, distort your view of the world. And this becomes really problematic when you're trying to ask meaningful questions, which, when you have a pandemic and you want to know what the causal factors are for the pandemic, you want to know what the prevalence is of the infection, that becomes important. So that's what I'm going to talk about. Now, this all started at the end of March this year when a group of researchers who were leading the COVID symptoms tracker app. So I'm sure many of you have heard of this, but basically it's an app that was developed by a company called Zoe and their collaborators at King's College London. And at the time, they had recruited about 1 million people within just a few days to report their symptoms in this app, which they wanted to then use to help monitor the spread of the infection and to make inference about what factors influenced infection. And what I'm going to do in this talk is talk quite a lot about this app and a lot of other data sources as well. And what I need to say at this point and make it very clear is that my personal opinion on the matter is that the researchers have worked unbelievably hard to really rapidly generate a platform which is secure and effective in collecting data very rapidly. And we've been in contact with them on a number of occasions, and they're absolutely committed to working hard and getting something good for the country. So what I'll be talking about is sort of flaws due to sampling bias, which are addressable. Um, and it's going to sound negative. I just want to make it clear that it's important to have that sort of discourse, but overall, it's vital importance that these sorts of epidemiological studies are being conducted. Um, so hopefully that hopefully that positive view on the thing is what you go away with um, at the end of the talk. All right, you're probably feeling a little bit of trepidation of just how bad it is that I'm gonna say that. I'm not. All right, so here's what happened in the end of March. They were planning to release their first batch of data to make it publicly available um, to researchers basically, and they had about 1 million samples, and they'd started doing analysis on it, and they just wanted to have an external view on whether or not the data was coherent. So they contacted us at the MRC Integrative Epidemiology Unit, and they just said, "We're going to be releasing the data in 36 hours. Can you just go through it, check what we're seeing is correct, and let us know before we release it?" So that was that was very exciting. Um, so at very short notice, we assembled a team. To look at this data. And these people who are listed here just dropped absolutely everything. Um, like they had childcare responsibilities and they fought through that to work on this data for 24 hours. And yeah, I was just incredibly impressed and proud of them. So all credit to them. Um, and what we did was we looked at various aspects of the data. We looked at whether or not the data looked like it was real or were people entering fake information. Um, and we looked at whether or not the system was parsing the data correctly, etc., etc. And one of the things that we also looked at was whether or not um, the data was representative of the population. So this is one view of the data and how representative it is. So this is a figure that is generated by Gareth Griffith. Um, and what he's done here is he's showed whether like the color code at the bottom there represents whether or not a, a location in the UK was over or underrepresented. And so what you see is this very strong patterning of where people are more likely to overrepresent an area in the app versus underrepresenting. So what we see immediately is that we're not getting a random sample of the population. So this is another way to look at that. What each, yes, it's all merged together because there's so many, but what each bar here represents is one region in the UK, and the axis on the y-axis is saying what's the odds ratio for an individual to be sampled um, into the app based on their location. So you see that some regions are extremely overrepresented and some regions are extremely underrepresented. And in general, the view is that you're generally over or underrepresented. Um, and So you can also superimpose on this the sort of socioeconomic position of each of those locations. And so one of the reasons that people are being over or underrepresented is because of their socioeconomic position. And it looked like we were getting much more sort of higher socioeconomic status individuals in the data. So we'll go on to talk about why that's a problem. But the take-home message here is that the samples in the data are not representative of the general population. Um, 20% of the variance is high, but that's not everything. So all the ways in which they're not representative is not known. And so now we're just going to talk about why this matters. Okay, so suppose that we wanted to estimate the disease prevalence from this data. Um, so how many people in the population have COVID-19 at any one time? So here's the snapshot of the data, and this is being done constantly, but just for illustrative purposes. So between the 3rd and the 11th of May in the UK, um, the COVID symptom tracker estimated that there were 225,000 people in the UK who were infected with COVID-19. And in that same period, the Office for National Statistics conducted a survey that said it was 133,000. Um, so the difference here is 92,000, and it's quite a large, meaningful difference. Now, the Office for National Security Statistics, ONS, they used a very strict random sampling procedure to estimate the prevalence. The COVID symptom tracker was trying to get as high yield as possible, and they weren't strict on who was able to enter. And we saw how non-representative that sample was. And so what it looks like is that if people had symptoms, they were more likely to participate in the app. Now, this gets worse when you consider the fact that the way in which the symptom tracker was able to evaluate if somebody had disease was through symptoms. So that's 225,000 symptomatic infections, whereas the ONS is estimating it based on testing. So that's all infections. Now, we don't know what proportion of the infections are symptomatic, but in the ONS study, they said 30% are symptomatic. So that basically gives us an estimate that the app data overrepresents COVID infections by 5 to 6 times compared to the general population. Is this important? I mean, in some ways it is. Like if you were worried about making policy based on the infection fatality rate, if you find that, let's say, some number of people are shown to have died from COVID-19 and the number of infections is inflated 6 times, that makes it look much less dangerous as disease. So getting this right is important. And yeah, so this distortion of our view of what's happening in the UK can arise from non-random sampling. Okay, so that's looking at sort of descriptive statistics. What I'm going to talk about now is an extra level of complication, which is asking how does this change our view of the risk factors for COVID-19? Now, it's hard to mitigate COVID-19 without knowledge of who to target, who's at risk, and it's hard to create cures for COVID-19 without knowing what pathways it's affecting. So knowing what characteristics of individuals relate to either COVID-19 infection or disease severity is crucially important in fighting the pandemic. So getting this right is really crucial. And what I'll show is how non-random sampling can induce spurious associations and make it very difficult to interpret any of this data. So before I go on, let me just give you a little bit of a primer on the idea of a dialectic acyclic graph. So these are used a lot in epidemiology to help a reader understand the assumptions behind any statistical model that is being used. Okay, so what normally happens is you have a square box which represents a variable, and arrows represent either a causal effect or something that you hypothesize to exist. So this is a classic example of confounding. And basically, suppose that we wanted to know what the effect of living in care homes is on being infected by COVID-19 infection. if we imagine that age influences living in a care home and influences COVID-19 infection, then there will be induced an association between living in a care home and a COVID-19 infection, even if there isn't a causal one. And if there was a causal one, it just distorts that association, so it becomes a biased effect. And the sort of the phrase correlation does not mean causation often refers to this problem, that you might have confounding, which leads to this association being distorted. So I'm not going to be talking about confounding much, even though that is a clear problem when it comes to analyzing COVID-19 data. I'm going to be talking mostly about selection bias. And so let's take an example which has been analyzed quite extensively now. So here's a question. Do ACE inhibitors, so ACE inhibitors are a medication used to treat high blood pressure. Did they increase risk of COVID-19 infection? Now, this was hypothesized, very sensibly because COVID-19, the SARS-CoV-2 virus, seemed to infect individuals through the ACE pathway. So, if you have ACE inhibitors, then that might affect how you get infected. So the hypothesis that was emerging was that ACE inhibitor use was increasing the risk of COVID-19 infection. And the sort of policy implication was that you'd ask people to maybe not use ACE inhibitors, which could be dangerous, and it could be practically challenging. So here's the problem that could happen. We're not talking about confounding in this case. We're talking about what's called collider bias. And collider bias is a special example of selection bias. Now, if we were to analyze, as we did, the relationship between ACE inhibitor use and COVID-19 infection, and we were to analyze that in the COVID symptom tracker app data, let's suppose that ACE inhibitor use influenced whether or not you contributed data, and COVID-19 influenced whether or not you contributed data. Now, with the benefit of hindsight, we can see that COVID-19 infection rates in the population seem to be very, very different to COVID-19 infection rates in the app data. So that is what is represented by this arrow. So we feel fairly confident that this is true. And we can also ask, what is the prevalence of ACE inhibitor use in the app data versus what we expect the prevalence of ACE inhibitor use to be in the population? And it seemed to be, let me see if I get this right. I think it was about double in the population compared to in the app data. So when you have two factors that influence whether or not you're in the data, they collide on the sample inclusion, and that induces an association between those two factors. So there might be a causal effect here, but when you look only through the lens of the data available to you, if they influence whether or not you're in the data, the relationship becomes distorted, and the distortion can be quite large. It can reverse the effect, it can attenuate it to null, it can create an effect where there never was one. So let's go through the intuition of why this is happening. So here's a toy example, and what we're going to look at is the relationship between physical attractiveness and acting talent. So this is an example that's used quite a lot. I don't know if it's a good one to use, but there we are. So let's assume in the population that acting talent and physical attractiveness are just not related. So you have this relationship, there's no slope that you could draw through this that would explain a relationship between them. But what if we only looked at individuals who had Hollywood acting careers? Okay, so let's assume that to have a Hollywood acting career, you either need to be very talented as an actor or very attractive. Now, what happens is amongst the people who are very talented as actors, they have average attractiveness. There's no reason for them to have higher attractiveness or lower attractiveness, as we saw from this graph. Um, Amongst the people who are very attractive, they have average acting ability. There's no reason for them to have higher or lower acting ability. When you ascertain and select only the individuals who made it in Hollywood, you find that this induces a negative relationship. Um, and when there's a negative relationship, the reason for that is that you either have to have a high score for one or a high score for the other, and that makes it look like one protects against the other. Uh, so that's basically the mechanism at play. And this is a very well understood mechanism. Um, to show you what it really looks like in real data, this is obviously a toy example. It's actually much more subtle. So here what we have is some data from the UK Biobank. And essentially what we're looking at is the relationship between age and adiposity. Now, if you look in adults over the lifespan, there isn't really a relationship between higher adiposity or obesity as you get older. But obesity influences whether or not you get selected, whether you get tested for COVID-19, and age influences whether you get tested for COVID-19. So if we take these data and restrict it only to individuals who have been tested for COVID-19, so in this data set of 500,000 people, about 2,000 people had been tested when this graph was made. Now, there is, where in the general population, the relationship is like pretty flat, this blue line. Amongst individuals who have been tested for COVID-19, the relationship is negative. So this is the illustrative view. What happens in data is much more subtle, which makes it much harder to know whether or not it's happening. Now, this association is large enough to be of interest because typically the associations aren't extremely large. They tend to be like fairly middling. But the point is that within COVID-19 tested individuals, there is a complete distortion of the relationship between different health factors. Okay, so just to give another example to illustrate how this has been thought about for a long time, the one classic example from health literature is this curious finding that if you look at low birth weight infants, maternal smoking seems to protect against infant mortality. And so this is a sort of inflammatory result that can arise from selection bias. So the intuition here is that there are two ways in which you can have low birth weight as an infant. One is because of maternal smoking, and the other is because of some illness that leads to low birth weight and leads to higher infant mortality. So maternal smoking probably does have a small effect on increasing infant mortality. But when you look at only the individuals who have low birth weight, maternal smoking is probably one of the better reasons to have low birth weight compared to the other bad reasons that could lead to low birth weight. And that makes it look like maternal smoking is those babies who have been exposed to maternal smoking have better outcomes than those babies who have illnesses that lead to low birth weight. So conditioning on a particular subgroup, when that subgroup is related to the factors that you're interested in, leads to a distortion of those associations. Now, I just wanted to put this in here because it shows that the relationship can be more complex than what I initially showed. What I initially showed was an arrow going from the risk factor to selection and from the outcome to selection. But it can be more complicated than that. There can be some confounder between the outcome and selection, which is just as good at introducing this distortion. Um, so back to COVID-19 and ACE inhibitors. So what did we find in the data? So we're asking the question, do ACE inhibitors use influence COVID-19 infection? Only able to get this within a sample who have contributed to app data collection. So the first data freeze, end of March, there were about 1 million samples, 38,000 self-reported having COVID-19. And that gave us an odds ratio of 4.1. So, oh, where have I gone? Yeah. So 4.1, that's an extremely large effect. And that looks very dangerous to use ACE inhibitors as it substantially increases your risk of being infected by COVID-19. So as time went on, a few days later, there's been a lot of press release about the app. There'd been a huge drive to recruit new people, and it grew in sample size from 1 million to 2.2 million. And when we reanalyzed the data, the effect of ACE inhibitor use on COVID-19 infection dropped from 4.1 to 1.95. And that shouldn't happen if that's a stable association. The odds ratio doesn't care about who's in your sample, like what ratios of people with ACE inhibitor use and COVID-19 infection, if it's not a biased estimate. The fact that it's so unstable is meaningful because what's happening is the proportion of ACE inhibitor use that is being represented and the proportion of COVID-19 infection that's being represented is changing, which changes the distortion. And if you go one step further and ask, amongst individuals who were tested for COVID-19, so that's a very small subset of the entire sample. So from memory, I think it's about 100,000 people of the 2.2 million. When you look at just the COVID-19 people who were tested, the odds ratio reverses and it makes it look like ACE inhibitor use is protected. So the point is that each of these different samples has a different pressure of selection into the sample. So being tested, you're a very special group of people. Being in the data, you're a different special group of people because you chose to contribute your data, and that comes with a whole host of other factors that we don't necessarily know about. So when you have such unstable estimates, the question becomes, to what extent can you explain the association that you see simply through collider bias? So there's a very nice paper by Grunwald, Tom Palmer, and Kate Tilling. Tom and Kate have been heavily involved in a lot of the work that I'm talking about as well. And what they did was they tried to come up with the mathematical derivation of what you would expect the odds ratio to be between some risk factor A and some outcome Y, assuming that the odds ratio truly is 1, so there's no effect, but A and Y both influence selection into the sample. So you don't need to understand this equation, but what this graph shows is that if you change the pressures for selection, so here on the x-axis, the effect of ACE inhibitor and COVID-19 on inclusion probability. So that's how much do the joint effects of having COVID-19 and ACE inhibitor influence whether or not you participate. And on the y-axis here is the effect of COVID-19 alone on inclusion probability. What you see is that this whole area of the graph gives you an odds ratio just due to this collider bias of greater than 2. And this area of the graph gives you an odds ratio of less than 0.8 just due to collider bias. So you can explore the area of, you can explore how likely, how credible it is that you could induce an association that you're seeing just because of some selection probabilities. And so this looked very dodgy to us, like that we couldn't really make a claim that ACE inhibitors were associated when it was so easy to induce those odds ratios just by selection probabilities. Okay, so another example that made a lot of news, smoking and the risk of smoking on getting uh, coronavirus infection. So here's an article in the New Scientist. And so the same question arises. What are the data sources and that are being used to estimate these effects? And what are the selection pressures into those data sources? So here's one example of a study that gained a lot of attention. So this was data collected in hospitalized patients in a district of Paris. And what they found was that amongst the individuals that were in the hospital, if they tested for COVID-19, smoking seemed to protect against COVID-19 infection. You were less likely to have COVID-19 test positive if you were smoking. Um, Now, so this is the basic question, like, does smoking influence hospitalization? And does COVID-19 infection influence hospitalization? And the answer is yes to both of them. So again, we can look at the graph and ask um, what areas of the graph could explain, um, of the parameter space, could explain the association that we're seeing. Um, and like again, we find that about 40% of the parameter space gives rise to an odds ratio that is greater than 2 or less than 0.5, just due to the sampling bias alone. Okay, so that's so again, like, it's easy to criticize those sorts of studies. Um, it's absolutely vital that those studies are conducted, but the question becomes, like, how meaningful are those estimates without performing a sensitivity analysis to evaluate whether or not um, non-random sampling can explain what you're seeing. Um, so one example of a study which has been, I think this is a really brilliant study. It could change the way that science is done in the UK for a long time. And it's the Open Safely study. And what they did was they linked primary care records from 17 million people to death records, death from smoking COVID-19, sorry, death from COVID-19. And in doing so, what you've got is a sample which is in effect representative of the population. You're not asking people to participate. You're not looking at only people in hospital, which is a very selective view of the population. You're looking at absolutely everybody who uses primary care, which is as good as random as you can get. So they've avoided this problem of non-random selection. And one of the analyses that they did was they were looking at the effect of smoking on death from COVID-19. So they're not looking at smoking on infection or smoking on death given infection. They're just looking at smoking on death from COVID-19. So it could be because it increases risk of infection or decreases risk of infection, or it could be because it increases or decreases risk of dying once infected. The study doesn't aim to disentangle those two questions. But here's what the result was. When you perform the analysis using just age and sex as covariates, so you're just adjusting for age and sex, it looks like smoking increases your risk of dying. When you adjust for a lot of other covariates, it looks like smoking protects against COVID-19. So this is where it becomes really pernicious. It's like really, really annoying. I find it annoying. There's this big debate in the statistical epidemiological literature. And the debate is this. If you have lots of variables, should you generally adjust for them? And it comes down to this. Now, if you say, yes, I generally should adjust for them, it's because you think they're confounded. If you think that there's lots and lots of confounders, then adjusting for as much as possible will reduce the bias here. Conversely, if you think that they're colliders, in that risk factor and the outcome influence those variables, then adjusting for them induces a bias rather than eliminating a bias. So how do you know what it is? How do you know if something is a confounder or a collider? So this is the crux of the debate. Is it better to agnostically adjust for a confounder, a covariate, so well, a variable, or is it better to not adjust? And you see the distant difference in the relationship when you adjust and you don't adjust. Like the reason that this is protective could be because you've taken away a load of confounders and it's truly protective, or it could be because you introduced a load of colliders and it's truly a risk factor. Um, so yeah, this requires a lot of care in analysis and reporting. Okay, so I talked about testing for COVID-19 being non-random, and I just wanted to like sort of point out the extent to which that's the case. So in the UK Biobank, we've got 500,000 individuals. This is a tremendously just, I mean, 3 years ago thinking about this blew my mind, and now we're used to this, and the next wave is going to be 5 million samples. But anyway, this is a great data set, and recently they managed to link those individuals to healthcare records to see if they had been tested for COVID-19, and if they had been tested, what were their results? So, if you were interested in using the UK Biobank to estimate an association between some risk factor and COVID-19 test status, you can only do it in those 2,000 individuals. Everybody else hasn't been tested. So you would be selecting based on being tested. So our question was, of the risk factors that you could potentially analyze in UK Biobank, and we chose 2,400 different variables. Of those, how many of them associate with being tested for COVID-19? And this is a QQ plot showing the result for that. And essentially what you've got on the x-axis is what you expect the p-value to be under the null hypothesis of no association. And on the y-axis is the observed p-value. So you expect that if there's no relationship between these 2,400 variables and being tested for COVID-19, the points should be along this line, but they're massively inflated. And if you were to set a strict threshold of whether or not a variable strongly associates with COVID-19 testing, 850 out of the 2,400 variables associate. And that includes everything from socioeconomic status to health status, behaviors, age, sex, genetic factors. It's a very wide range of things. So we need to take care in analyzing these. So just a quick point about prediction as well. I've been talking about looking at causal factors for COVID-19. Prediction is a little bit more tricky. We don't necessarily care about finding a causal factor when trying to make a predictor. To give a trivial example, yellow fingers might make a good predictor of lung cancer, but that's because smoking gives you yellow fingers and smoking gives you lung cancer. Nevertheless, it still predicts whether or not you're going to get lung cancer to some extent. So you don't care if it's causal. In the same way, colliders could help you make a prediction better than if you were just restricting to causal factors. The low birth weight amongst infants is a good example of that. Like if you found that some of the individual, if a baby had low birth weight and you found that the mother smoked, I mean, you'd sort of maybe feel a bit relieved because that suggests that it's not something worse than smoking that caused the low birth weight. So it's predictive of mortality. So prediction, it can help, but there's a caveat to that, and it only works if the sample that you want to predict has the same selection pressures as the sample that you use to train the predictor. Okay, so here's an example of a predictor. Again, this was developed using the symptom um, tracker app, and they found that there were a bunch of different symptoms which were good predictors of testing positive. So they've got 2 million individuals, about 100,000 of them have actually been tested for COVID-19. And so amongst the 100,000, they can find what predicts being tested positive versus testing negative. And they find a bunch of different factors. Um, and essentially, these look like reasonable factors. They look like they are actually going to be, that they're sensible things that probably do predict whether or not you have COVID-19. Um, the problem is though that you have to make weights for these factors. So anosmia, which is loss of smell, like what is the correct weight for it? Persistent cough, how much does that predict being testing positive, chest pain, etc. And Matt Tudball did a simple analysis here where he basically said, I'm going to reproduce the summary data for this whole sample and demonstrate that no matter what the true odds ratio was for each of these factors, I could induce what was observed in the data just by changing the selection probabilities. And the take-home message here is it's only very subtle changes in being selected into the sample that can like make a nudge ratio go from 2 to 12 in your data. And and the consequence of that is that even though you have the factors correct, if the weights are wrong, you will overestimate how good a predictor that's going to be. So in your sample, it might have an area under the curve of close to zero point 0.9. But when you move to a sample that doesn't have the same selection pressures, which is basically everybody who hasn't been tested, who are the target of your prediction, the area under the curve can drop quite drastically. Okay, so very quickly, I just want to talk about one more thing, which is a little bit more complicated. I just wanted to like point this out because it's being analyzed a lot in the literature. So what about analyzing survival amongst those infected by COVID-19? So here's a good example of a study that did that, and they concluded that ACE inhibitors protect you from dying if you've been infected. So let's just like look at that a little bit. So suppose that ACE inhibitors. So our question ends up being, if you were only looking at people who have been infected, that's a selection into the data. It's a specific type of selection known as index event bias. And everything that associates with being infected now might look like it protects against severe outcomes having been infected. So an example here might be ACE inhibitors. Amongst the people who get hospitalized and are being analyzed for being infected, they probably look better. They look healthier than the very frail individuals, and who are also being hospitalized. So when you compare ACE inhibitor use against everybody else, they might just look like they're healthier and therefore they're protected against dying. So this is an extra complication on the collider bias issue. Okay, I've a few minutes left. I'm just going to very quickly talk about things that you could try to do, but the upshot is that it's really hard to avoid it. So the ideal thing is that you recruit people who are representative of your target population, but this is very hard to do. You might invite people at random, but only a particular subset responds. This is true of UK Biobank, who are very enriched for people who have higher socioeconomic status, higher education, etc. You might recruit a representative sample, but individuals drop out non-randomly. So this is true for ALSPAC, who recruited everybody, every pregnant woman in the Avon area, and that was about 12,000 women. And today, only about 5,000 remain, and they're a very selected sample as well. So I'll just skip this because it's a little bit complicated given the time. But the point being that if you could actually potentially use dropout rates to try to extrapolate back and understand what the effect was, even if you had non-random sampling to begin with. Um, okay, so um, yeah, so aside from that, once you've got a sample and you're worried that it is actually potentially non-random, and you want to guard against this problem of collider bias, the first thing to do is just to compare your population descriptive statistics against the population, against the sample. So is my age and sex roughly representative? What about the risk factor? Is the rate of this drug use in the sample the same as the general population, etc.? The next thing to do is to ask, if they're non-random, how credibly could they explain an association that you're viewing? So we looked at those graphs, which are a bit complicated, but they give you a view of just how easy it would have been to induce the association given the selection you're viewing. And then there's more sophisticated analyses again that you can do. So there's one in particular which is important to do, which is called inverse probability weighting, and that's where if you know that there's a demographic in your population that is underrepresented, then you give them more weight in your analysis, which tries to bump up their representativeness in your sample. The problem that this could arise from this is that you have a poor model of what is representative in your sample. If you have a misspecified model of representativeness, then you could actually make things worse. That's really difficult also. So just to summarize, like it's crucial to collect this kind of data, but across almost all the designs that we've looked at, there's like a pretty good chance that the data is non-representative. Um, and therefore that can distort associations to a pretty large degree. So my advice to you, and this is what I do and what my colleagues do, like whenever they're reading any study that makes a claim about a risk factor for COVID-19, you hit Control and F in that study and you search for collider, you search for selection, random, participation, representative, etc., and just see what they've done to address this problem. The vast majority of studies are not doing anything. And if they haven't done anything to convince you that they tried to account for the non-representative sampling, then like just how credible are the conclusions? All right, so there's lots of further information on this. There's this paper which goes into the inflexive bias problem in particular detail, a couple of blog posts, and this work has been a joint effort. It's been great working with all of these people. I won't name them all, but thanks to them. And thanks to the MRC, Royal Society, and Wellcome Trust for funding. Thanks to JGI for giving me a chance to talk to you about this.
Thank you so much. That's great. One of the weird things about doing these talks is you don't hear the round of applause. So I shall give you a little round of applause myself. That was really interesting. I'm mindful of time and that we have another lecture starting at 11 that some people may be wanting to go to. But we do have a couple of questions. So we've got, I don't know if you want to flick to the chat. You can read it for yourself, but we've got one from Samir. Can you go over again the idea of the benefit of using controls if you think the relationship is confounding, but that it would be detrimental if the relationship is a collider one? Quick recap, if that's possible.
Yeah. Is it this one?
Yeah.
Yeah. Okay. So suppose that amongst our data, let's say, so this is a little bit tricky because there isn't actually an arrow from COVID-19 death to a collider. There's going to be something something that influences COVID-19 death and the collider. So let's suppose that it's care homes. Now, care homes could be a confounder. That means that they influence smoking and they influence COVID-19 death. Or they could be a collider, which means that they um, so like they relate to COVID-19 death. Um, oh gosh, but yeah. And so if you adjust for it, then you have a decision to make whether or not like that was actually something um, which influenced um, which is being influenced by selection into the sample, or whether or not it's actually influencing both of the risk factors. So essentially, in general, you don't necessarily know whether or not something is is a consequence of the two risk factors that you're looking at, or if they're causal for the two risk factors that you're looking at. But having looked at this, I think I could have made this much clearer by thinking about something that is more concrete. Sorry about that.
Okay, and then just very quickly, we had Paul Ross from our own library services asking whether more replication studies could mitigate against possible collider bias, or whether you think this needs sustained better data gathering practice from the start. I suspect you're going to say the
Yeah,
latter, but I don't know.
yeah. So one of the big things that you could do with replication is that you could have a different set of sampling. Um, so a different set of sampling mechanisms. So suppose that you try to replicate your result from the app data from results from hospitalized individuals, and you find that it's consistent, then you might argue that there isn't really a selection bias which is leading to the result, because you're finding consistency across different forms of selection. So that could be really useful. Um, and in general, it's important to replicate your results as well. One thing to bear in mind, which is related to this, is that increasing sample size is not a solution. So when you think about epidemiology and these sort of statistical models, the consequence of increasing sample size doesn't eliminate bias. It reduces imprecision. It makes your confidence intervals narrower. So the consequence of that is that you become more certain about the wrong answer if you've got selection. Um, and so, yeah, so the study design is probably more important than the sample size, and replication is a good way to think about it.
Interesting, thanks. There are a couple more questions in the chat, but I think we've run out of time. It just shows how well received the talk is. We've had loads of people visiting and loads of conversations going on in the background. So thank you so much, Jib. That was great. And to
Thank you.
everybody, thank you for joining us. Remember that you may get a feedback request. It'd be great to know what you thought, and if you've got any suggestions for the future. Do share your attendance on social media. Give us a shout out. Many thanks to both our speaker and Gibran Hemani, but also our helpers behind the scenes, who today were Liz and Lily and Patty. So thanks to everybody. Stay well. Hope to see you at some of the other events this week. Bye for now.
Thanks. Bye then.